Alright, and welcome back, and this is the Chipmaster, and in this class we're going to look at the RAM or memory action important signals, memory important signal action timing. Right, so in this class we're going to talk about a little about the RAM, right, and each individual section of the RAM slot and how the RAM works on the laptop notebook motherboard. Alright, so remember this is a demo video. If you want full videos you will have to pay, so by the ending of this month my video should be fully launched, so you can have them ready. I will have them ready for purchase. Okay. Alright, so this is the system memory DDR2 and DDR3 signal groups. As you can see, we have a set of group of signals, like we have clock, we have data, control, and command, and miscellaneous. But we're going to focus on these first four group of signals, and this is the signal name. We have DDR2, right, CK, which is for clock, which is 5 to 0, which is a system memory differential clock. DDR2 requires 3 pairs of clocks per DIMM, right. I have here a schematic of a schematic here of an ASA Aspire 5745, which is the IBEX Peak Intel Series 5 chipset, right. And we're going to go to the RAM page, which is on page 14. Alright, so we have page 14 here. Alright, so this is the slot. This is your DIMM slot, right? 2 slots. Alright, so this is JDIM2A, as you can see, and this is JDIM1A. Alright, so this is your slot. Alright, so we have here as you can see, the RAM slot is divided into several sections, as you can see, right. We have the address. A stands for address, and this is a one-way communication from the CPU. Remember the CPU, the Arundel CPU, this is the Arundel CPU. So the Arundel CPU has the memory controller that's integrated inside of the DIMM slot that's inside of the CPU, because this CPU slot has this CPU has some parts of the north bridge function, right, inside of the CPU, and the remaining part of the north bridge is inside of the PCH, right. So this is the integration coming over to Intel Series 5, right. This is the difference between Intel Series 5 from Intel Series 4, where they integrate some of the north bridge function in the CPU and the rest of the remaining functions inside of the PCH, which has some south bridge function and a little bit of the north bridge function also, right. As you can see, this is a dual channel DDR3, which is running at a 800 to 1066 frequency speed, bus speed, and we have 2 slots, right. So let's go back to the slots. Alright, so page 14, sorry. Alright, so we have here the A. This is the address bus. So the address bus that's inside of the CPU, and we have from A0 to A15. So if we go back to the handout, we have the address bus here, right. And the address bus, as you can see, MA DDR2, and this is from the command section. So DDR2 and DDR3, right. But for now we're talking about the clock. So DDR2 requires 3 pairs of clocks per DIMM, right. And DDR3 requires 2 clocks. So DDR2 requires 3 clocks per DIMM, DDR3 requires 2 clocks per DIMM. So if we go to the schematic, this is a DDR3 board. Remember, we have the clocks, and here they are. So CKE0, right. So let me CK0. So CK0 is here, right. CK0, this is 1 pair, right. This is 2 pair, CK1 hash, positive and negative, CK0, right. CKE, this is CK, this is the clock. So we have 3 pairs of clocks. So we have 1, this is 1 pair, right. This is 2 pair, and this is the clock enable, right. So that's 3 pairs of clocks, 2 pairs of clocks, right. So if we go to the handout, see, DDR3 requires 2 pairs of clocks, right. And here are the 2 pairs of clocks. Let me highlight it. So this is 1 pair, see, CK0 hash and positive, CK0 positive and negative. So that's 2 groups. So that's 2 pairs of clocks, 2 clocks coming to the RAM slot, as you can see. So this is a DDR3 board. Remember, this is a DDR3 based board. Alright, so that's 2 pairs of clocks, right. So this is the difference between DDR2 and DDR3, right. So the next part we're going to look at is the data, and this is DDR2 and DDR3. If you notice, we have DQ stands for data bus, right. So DQ0 to DQ63, so that's 64 bits in total. Here they are, right. And I see this is the data section, right. And as you can see, this is a bidirectional communication between the CPU and the RAM slot. So the memory controller inside of the CPU is communicating with these pins, and this is your data section. See, DQ0, right, all the way down to DQ63. So that's a total of 64. As you can see, 64 bits of data that is transferred, right? 63, 0 to 63, DQ, right? And that's the data bus. So you, when you boot up your machine during the maintenance process and you check these pins, you should see a significant waveform, right? As I said, this is a demo video. If you want full videos, you have to pay, right? So I will show you when you pay in practical and in theory. All right, so this section here is the data strobe or data section. So this is, you can check any one of these pins to see if there's any waveform. That means everything is okay with the CPU and the RAM. All right, so we have here also DM, which stands for data mask, right? So data mask, which is an output only, so it's total of seven bits, total of 7 bits. So let's go back to that section, and it's down here, right? See, DM0 to DM7. So this is a total of 8. So right, so that's 8-bit output. So it's an output only communication. See, DM7 0. So this is an output connection, right? This is an output that is going. So sometimes the schematic will make some errors, right? So this should be a different section from like this one. So sometimes the schematic have some errors, so we have to correct the schematic. Right, so this is an output only, as you can see, output. The next one we have DQS, which is a data strobe. Data strobe, DQS. Here it is, DQS, that's 0 to 7, that's one group. 0 to 7, this is positive, right? So one side is positive, so this side is the positive side, right? That's one group, and this group is the negative. There's a hash, the hash. This is the hash sign that makes it negative. So this is negative and this is positive, as you can see, right? So this is data strobe, DQS, which means data strobe, right? And as you can see, it's a total of 0 to 7, right? 0 to 7. So this is so this is your address bus. This is your address bus, right? This is your control bus. Now there's a very important signal that I want to show you, which is the ODT0, ODT1. This is known as on-die termination. So let's, if I go, and this is a part of the control section, as you can see, right? So we have CKE, CSB, which is the clock enable, 1 per dim rank, CSB, which is a chip select, 1 per dim rank, and then we have the on-die termination. So here is it, right? Chip select, just like your BIOS chip. On our BIOS chip, we have a chip select signal, right? So here we have clock enable, CKE0, CKE1, very important signals, right? So you should check this signal first during the maintenance process. This is about 0.7 volts. This is your on-die termination. This is about 0.7 volts, ODT, right? So your ODT, right? So this section is your on-die termination, and this is coming from the memory controller inside of the CPU, and this is coming here, while at the same time we have SDA, and SDL, which is the SM bus to read the EEPROM chip on the RAM. On the RAM, there's a small EEPROM chip on the RAM that stores certain information like the manufacturer's information, the speed of the RAM, the frequency. All of that information is carried through the SM bus, which is this clock and data, which is a two-wire communication, a bidirectional communication, right? So once this signal is coming, then on-die termination will rise first, then after you will recap the SM bus after a few milliseconds. So this is the timing. If you want to get the correct action timing, you can check on-die termination with SM bus, the clock, the data, sorry, and then you will see the difference in your timing. So on-die termination will rise first, and then second, the SM bus data, serial clock data will rise. So the CPU reads the RAM. So this signal is the drive signal. If this signal is not coming, then you will have a no display fault or an error, depending on the manufacturer of your notebook motherboard. I wonder if you understand what I'm trying to say right here. So the on-die termination, which is about 0.7 volts, which is going to here from the memory, from the memory controller inside of the CPU, Okay, so that's the on-die termination, and this is a part of the control bus. So the on-die termination, we have clock enable. This is your control bus section. So let's go from the top. So we have address bus, we have data bus over this side, and this is the control bus, right? So this is the steps of how to check your RAM slot, right? So this is a data mask. This is an output only connection section, right? And this is data strobe, right? So this is the steps that you're going to know how to understand how the RAM works. So first you must get on-die termination. On-die termination of 0.7 volts, right, should come here first, right? So let's go to the handout. So we have the on-die termination, which is an on-die termination which is 1 per dim rank, right? We have chip select, right, which is a chip select, because remember there's an EEPROM chip on the RAM, so it must have a chip select, and the clock enable, which is 1 per dim rank, and one chip select, and chip select, that is 1 per dim rank, and on-die termination, which is also 1 per dim rank. And I explain the next one, which is a command. We have DDR2, DDR3, we have MA. This is, as I said, a part of the address bus, right? MA, right? See, 0 to 14, 0 to 15, right? That's your address bus. All right, and we have BS, which is a bank select, right? We have bank select, right? Here it is, BA. This is the bank select, which is a part of the bank, which is a part of the control bus. Okay, then we have RAS, row address select, and CAS, which is column address select. So column address select and row address select is right here. See, column address select, row address select. This is a part of the control bus, right? And write enable, WE. So the write enable signal is the last signal that will come only if DRAM reset comes high. Once DRAM reset comes high, then write enable will execute immediately. So this signal DDR3 underscore DRAM reset of 1.5 volt, which is coming to pin number 30 to reset the RAM, then the write enable signal will in action. So first we have 1.5 volts. Sorry, this should be pull low. So when it is pull low for a millisecond, it rises back to steady state. Then after, the write enable will start its action. So this is the write enable, right? This is write enable. So write enable will immediately come in effect after this 1.5 volt is pull low. So this comes first, then this signal comes first. So if you want to confirm with oscilloscope, you can try it and you will understand. So DRAM reset must pull low for a millisecond, then immediately write enable will come. So this is a hash which is active low. So the write enable signal is a low signal that is active low once DRAM reset is pull low for a millisecond, right? In the practical, you will get a better understanding, and you will understand better when I show you practical on how this is done, right? So let's go back to the handout. Let's go down, right? So the memory of several important signal action sequence are basically as follows, right? First, we have the power supply, which is 1.5 volt VTT power supply. We have 0.75 volt, which is the reference voltage. Remember, this voltage is half of the original voltage, so 1.5 divided by 2, we will get 0.75. This is for DDR3, right? If it's a DDR2, it's 1.8 volt, so 1.8 volt divided by 2, you will get 0.9 volt, and so on for DDR4 and DDR1. So this is the half of the reference voltage, right? So your reference voltage is your termination supply voltage, which is half of your reference SMD and the SMDDR underscore VREF underscore dim, which is your reference voltage of 0.7 volt. As you can see here, it is SMDDRF 1.5 volts. This is coming to a voltage divider. As you can see, it's not connect. These resistors are not installed. So R128 and R129 is not installed, and it is pulled up and it is coming, but it is 0.7 volt SMDDRF, and it is 0.7 volt, as you can see, coming to here after being renamed. So it's first named as plus SMD DDR underscore VREF. After coming through a short resistor here, it becomes SMDDR underscore VREF underscore dim, and it's coming to pin number 1 and pin number 26 of the RAM slot. Here it is again, 0.7 volts DDR VTT, right? So this is the main reference voltage, VTT. Alright, so power supply, mean power supply from memory, 1.5 volt VTT power supply. So this is the VTT power supply of 0.75 volt, which is the RAM termination supply, right? After 0.7 supply, there is another. This is a SPD. SPD stands for serial presence detect chip, which is the chip. This is the SPD chip on the RAM. This is 3.3 volt power, which is the SM bus pull up voltage, which is a memory controller of 1.5 volt supply, etc. Alright, so this is the supply of 0.75 volt SPD chip. SPD stands for serial presence detect, right? And this chip is on the RAM chip itself, right? And it has a supply of 3.3 volt. Right, the SM bus pull up voltage and the memory controller voltage is 1.5 volt. Right, so the SPD chip is that small chip, see, VDD SPD. Right, this is the voltage supply for the VDD SPD. This is your main power supply of 1.5 volt. Right, this is a 1.5 volt, and this 3 volt run power, which is a VDD SPD serial presence detect power supply chip. Alright, next we have ODT, which is the termination resistor that's inside of the memory controller. This is used for impedance matching, right? So of the memory bus, data bus reduce signal reflection. So this is why on-die termination must comes first at 0.7 volt. When the signal is low, the memory controller cannot drive the signal and the file error will appear. There's an error will appear if the signal is not drive or pull low, right, to about 7 volt. Then you'll have a fault, right? So the termination resistor under there's a termination resistor inside of the CPU also. So this is the CPU, right? This is the CPU, and this is the RAM slot. This is a RAM, right? So this is the CPU, right? And this is the RAM, and this is a RAM. So there is a bidirectional communication between the RAM and the CPU. The memory controller in the CPU, there's a bidirectional communication between the RAM and the CPU. So understanding how this works, so this is the CPU, this is the RAM, right? And there's a communication between the RAM. So inside of the CPU you have a resistor, which is a termination resistor that's inside of the CPU, right? There's a termination resistor that's inside of the CPU, and this is to prevent signal reflection because you don't want to lose the data. So you must have to find a way during the transmission of data, and the data is transferred in like something like right, so the data is transferred in bits like this, right? When the RAM is communicating with the CPU, right, we have positive and negative of data transfer. So positive, negative, positive, negative. Now during this high speed, this is a high frequency transmission of signal going back and forth. When the CPU is returning that information back to the CPU, if the ODT section in the CPU is not in the memory controller, the RAM termination resistors and section inside of the RAM is not working, then the signal will be gone. When the signal is being transferred back, when the CPU transfers the signal, when the CPU transfers the signal back to the RAM, the data will be lost. So this is why you have an internal resistor that's inside of the CPU, and there's a termination resistor on the RAM, right, to prevent, and this is known as impedance matching, right? To prevent signal reflection, so you don't lose your data. So that is why it has a termination resistor, and the on-die and the ODT section inside of the CPU and the RAM, sorry, is to maintain that data and you don't lose your data, and that can cause all different kinds of indescribable faults such as hanging, blue screens, all different kinds of problem that is occurring because there is a fault with your termination section on your RAM, right, or during the transmission of data, right? So this is something that you have to pay attention to, right? You have to pay attention. So this is why we should know and understand the working principle of the RAM. So as I said, when the communication between the CPU is coming like this, right, one positive, negative, right, so this is a positive, negative, a positive, a negative, a positive, and so on, then the CPU, if this is a fault, then the data will drift, 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 and all kind of problem will occur. Alright, this is a demo video. If you want full videos, then you have to pay. Right, I hope you learned something from this video, and thanks for watching. Thank you.